Hello, ladies and gentlemen, and welcome back. We are going to be finishing off our 2013 Canadian Open contest in this video. That's right, we're looking at C4. Alright, so what have we got? For each real number x, now this isn't the floor or the ceiling function. This is the integer part function, I think. Let square brackets x be the largest integer less than or equal to x. No, I guess this is the floor function. They're just not writing it like that. Weird. Okay. That's fine. For example, floor function of 5 is 5. I'm going to call it floor function, by the way, but usually it's written like this. Floor of 7.9 is 7 because 7 is less than or equal to 7.9. It's also an integer, and it's the biggest one of them. And the floor function of negative 2.4 is negative 3. An arithmetic progression of length k is a sequence a1, a2, all the way up to ak, with the property there exists a real number b, I prefer to call it d, call it O for the common difference, such that each next term subtract to the current term is equal to b. So, in other words, if I want to figure out ai plus 1, I gotta rearrange this and say it's just the last term ai plus this constant b, this fixed common difference. Alright, let alpha be a given irrational number. Okay, and it's bigger than or equal to 2. Then S is the set of floor functions of n times alpha, where n is just an integer. So this is a set of integers. It's all the set of all integers that are equal to the floor of n times alpha for some integer n. Okay. Prove that for any integer m greater than or equal to 3, there exist m distinct numbers contained in S which form an arithmetic progression of length m. Okay. And B part, prove that there is no infinite arithmetic progressions contained in S. So eventually they all stop, but I can get one of any length that I desire. Okay, so it's a subtle difference in the two. Okay. You can't just say, well, in part A, you can make them as big as you want. Yes, you can make them as big as you want. You can make them 10 terms long, or 10 million terms long, or 10 trillion terms long, but you can't make one that's unending. Okay? It will always end. Alright, so how do we actually get integers out of here, and how can we get an arithmetic progression? Well, I think maybe one of the easiest things to do is just look at two terms. We'll try and be very simple. We'll just say, you know, let's look at n plus 1 alpha minus n alpha. Okay, is there anything that we can say about that? Well, if that's equal to some number b, what must we have here? Well, this one here is the same as n alpha plus alpha. So you might think that, oh, this should break up into n alpha plus alpha. Now this isn't quite the case. It's close. It's either this or it's, I think this. Might be a minus 1 case as well. Be really nice if I could use my calculator, because then I could write out some examples and work with those, but alas, we do not have calculators available on the open. So why this plus 1 here? Well, if things are big enough, if n plus 1 is big enough, so maybe, oh, what's a good number to use? I don't know. Let's say root 2. I'll try and illustrate why I think this is the case for root 2. So root 2 is about 1.414. And if we double it, So the floor of root 2 would be just 1. If we double it, we get about 2.828, plus, plus some other stuff. And so that's a nice arithmetic progression of 1 there. But if I did 3 root 2, then we'd be looking at 4.242, and that would jump up to 4. It wouldn't go up by 1 again, as you might expect, because this other part here, the leftover part, the decimal part, has actually managed to get big. And I think that might be a good idea. Let's say something like, let alpha equal a plus, what's a good other letter? I don't know, beta. Alpha plus, let's let alpha equal a plus beta, where a is sort of what's left over, and then therefore beta is, it's going to be irrational. And more importantly, beta is bigger than 0, less than 1. Then n alpha, it looks like na, that's a fine integer, plus n beta. And so n alpha should just be na plus whatever the integer part of n beta is. And depending on, so for root 2, this beta part is about 4.14. I think the next one's a 2, 41423 or something like that. I don't know. I don't have it memorized, and I really don't want to get out my calculator because I shouldn't be using that. Okay, but eventually this beta, because it's not 0, you keep multiplying it, eventually it's going to sort of spill over beyond 1, and you'll gain another sort of integer part. So, what can we do? We want an arithmetic sequence of length m. So if, for example, if beta, 2 beta, 3 beta, and so on, all the way up to m beta, are all 0, because the original beta is 0, are all 0, then alpha, 2 alpha, and so on up to m alpha are an arithmetic sequence of common difference a, because this one would just be a, this would be 2a, and so on, because the leftover part, when you multiply by beta, we're saying suppose that amounts to nothing. Now, this is not something that should be true, and certainly you can't say that this is true for any beta, but this works. So beta, 2 beta, all the way up to m beta are 0 if beta is between 0 and 1 over m. Since then k beta is between 0 and km, which is less than 1, well, less than or equal to 1 for all the k's between 1 and m. So, but the problem is they don't tell us anything about alpha. You give me an alpha, and sure, maybe I can get you a sequence with m is 3 or 4, because the given alpha has this beta that's small enough, but what should we say? Alpha is fixed, and so its beta is fixed, and that's going to run into a problem, because eventually there will be some n that we choose that is naturally less than that. So we've got a bit of a problem. For root 2, the beta part here is less than a half, which is why I can get an arithmetic sequence pretty quickly of 2. But it's not less than 1/3, which is why after 3 times root 2, we get this jump. But if I used something like, root 5. So for example, if I used something like root 5 is about 2.236 or something like that. And so the beta here is definitely less than 1/3. So I can confidently say that 2 root 5 and 3 root 5 will form an arithmetic sequence of length 3, but and one of length 4 because this is actually less than 1/4, but not one of length 5 because this is greater than 1/5. Okay. But for something like the golden ratio, which is 1 plus root 5 over 2, looks like 1.618, you're going to have none of these. No arithmetic sequences. So that's our new challenge. I know how to make an arithmetic sequence if the beta is small enough. Now, what else can we say? Well, if alpha is irrational, then so is k alpha for any integer k. Because if you could multiply it by an integer and get something that wasn't irrational, then you wouldn't have something that was irrational to start off with. Irrational means that you can't write it as a ratio. So it's not. It doesn't look like it doesn't look like p over q. But if somehow k alpha was equal to p over q, then alpha would look like p over kq, and that would be a ratio. Now, you wouldn't need to write that reasoning. You just need to say you can't. Any integer times an irrational is still irrational. So my thinking is, if we pick the right k, maybe we can make this beta part go between 0 and 1 over m. Okay, so what to do? How would we go about showing that? Well, I think I'm going to use some notation. Now, this is notation I've learned from an upper year course. It was a grad level course, actually. You don't have to use it, but I would just make up my own notation. And what I'm going to do is say, and it's perfectly fine to make up your own notation as long as you clearly explain it. So for any irrational number, x, let squiggly x be x minus what they're saying is the floor function. I disagree with this notation. That's okay. So this in a sense is my beta. Okay, so this guy here is my beta. And what I want to do is say something to the effect of the integer part of k alpha well, what can we say really about it? This is the challenge. I want it to fit between 0 and 1 over m, and so in theory this should work. But multiplying it by k, you might go over. And so this is I think this is true. Yeah. Because the integer parts don't matter when we write things like this. I'm not necessarily sure this is going to help me, though. Well, let's say something like this. For alpha and a given choice of m, we can find integer, I don't need an S, integer k, so that k is equal to 1 of 0 up to m minus 1, and k over m is less than, this beta here is less than k plus 1 over m. So what we're really doing is we're sort of chopping up between 0 and 1, and we're fitting beta in somewhere in here. Okay, so then what happens if I do 2 beta? Well, unfortunately, the gap sort of widens. So I don't like that. So, okay, this doesn't seem to be working. Let's try something else. Well, let's look at the first m plus 1 multiples of alpha. Now I'm choosing m plus 1 because what I'm going to want is sort of an overlap. So this is alpha, 2 alpha, and so on, all the way up to m plus 1 alpha. Then there are m intervals 0 to 1 over m, 1 over m to 2 over m, and so on all the way up to m minus 1 over m, all the way up to m over m. And there are m plus 1 decimal parts. Alpha, 2 alpha, so there's got to be 2 of them that are in the same sort of bucket. There could be more, but there's got to be 2 that are in the same interval. This is what's known as Pigeonhole Principle. So there must be P and Q. We'll say Q is the bigger one. So that P alpha, the fractional part of that, are in the same interval. Okay. So we can get 2 of them together, and I think we should be able to assume that if I take the difference, it should be less than. That's what I'm thinking. So I don't know which one of the fractional parts is bigger, but I can definitely say this. Okay, the difference between them is 1 over m. Okay. Then what else could we say? Well, can we change this to the betas? I was really hoping that having two of them close enough would make things work. But I'm fairly certain I can't just combine the two. Can I? Well, let's say this. We see P is less than Q, so P alpha is less than Q alpha. So fix integer, what haven't I used yet, R. And that'll be Q alpha's integer floor function minus P alpha's floor function. So I think we can add to this. So if Q alpha minus P alpha is between 0 and M, then I could add on to both sides. What did I just call it? R. So this will be minus and that'll be less than R plus 1 over M, which kind of got squeezed in here, so let's write it on another line. R plus 1 over M. So then Q alpha minus P alpha is between R and R plus 1 over M, and now I have, there we go, now we can factor this out. And a similar argument holds for if it turned out that for some reason the fractional part of P alpha was the bigger one. So what are we going to say? We'll say, well, I'll flip it around. And then we're going to add negative R to both sides. Okay. So in either case, we can find integer k. So the fractional part of k alpha is between 0 and 1 over m. And as already remarked, it was way, way back when, but you'll get an arithmetic sequence then. K alpha, 2k alpha, all the way up to mk alpha are equal to 0. Or no, they're not equal to 0, but these guys form an arithmetic sequence. And I don't think we really need to reiterate this. So it's because the fractional part is less than 1 over m, then the fractional parts of 2k alpha and mk alpha, they will also be between 0 and 1. Yeah, I suppose we could write that, so. Well, no, the fractional parts are always between 0 and 1. So what's the actual argument? I guess it would be 0 is less than k alpha less than 2k alpha. So I don't multiply inside because otherwise fractional parts are always. So it's m k alpha, but this would be less than 1. Okay. So there we go. So the fractional bits here. This will be 2k alpha. And this will be mk alpha because it doesn't overrun and then then lose an integer part or anything like that. Okay, so there we go. Got an arithmetic sequence plus a little bit of extra explanation at the end there that I don't think is really necessary. So that was a part. Now show there's no infinite arithmetic progressions. So the question is, how should we do that? So should we do a proof by contradiction, assume there is an infinite arithmetic progression? Well, I can't think of another way to start it. And I think we might need to use this fractional part, this notation, that I'm borrowing from a grad level course in my master's. But of course, you can make up your own notation. I think this is the standard way of saying the fractional part, but not like it comes up that often. Yeah, I think it might be best to do that. So let's say, suppose there is such an arithmetic sequence, and it has common difference. I'm going to use D. They use B in the statement, but I like D. So common difference D. Well, then what can we say? So should D be some sort of multiple of A or something like that? So then there is, let's say, n1, n2, yada yada yada, integers. So that ni plus 1 alpha minus ni alpha is equal to D. Okay, so that's what we're saying there. So can we rearrange this? So then ni alpha plus D is equal to ni plus 1 alpha. Now, if you've got an integer and you add it to an integer part, so for example, if I did something like 5.2 plus 3, that is always the same as 8.2 floored as well. So you can always bring integers in and out as much as you like. The question is, could you do more? So I guess we could pull this in. So if they're the same integer part, then n plus I alpha minus D plus ni alpha has to be between 0 and 1. Right? Don't know if that's the best way to write that conclusion. But basically, they go to the same integer. So let's... No. Let's say... And let AI be ni alpha integered. So this is alpha, this is AI plus 1, so then AI plus 1 is less than ni alpha plus d. So less than or equal, but it should be less than because we've got an irrational part here, so actually let's drop the less than or equal. And this is less than AI plus 1 plus 1. Okay. Yeah, I don't know whether or not that was better than, or if just writing... Because we don't know which one's bigger than which, so... I guess we have this range here. And that's about it. But then we can regroup and say ni plus 1 minus ni alpha minus d is less than negative 1. And then I guess we could add d to both sides, but I'm not seeing exactly where this goes. So this is true for all integers I guess, but so what? I see no reason to think that this can't happen. So, and if I think that's the case, if I see no reason why this can't happen, then surely I should be able to construct one for something like root 2. Construct an infinite sequence for root 2. I suppose we could bring back our betas. I'm also going to flip the sign around, just because I feel uncomfortable having the big things on the left. So this is an integer, and then we also have this. So, what to do? Well, I feel like there's only so many integers k I can multiply alpha by to be in this range here. And there might be more than one, but... Oh, wait, no, because alpha is greater than 2. Right? So we might actually have to use that fact. I thought it was kind of odd that they gave us alpha greater than 2 as an irrational number, because really any irrational number should have worked for the first part, but maybe now is when we use alpha greater than 2. So I would say something like, clearly, ni plus 1 is not equal to ni, because then that's not an arithmetic sequence. Now they say m distinct numbers contained in S, and then no arithmetic progressions contained in S. I assume they mean that the same number can't be used more than once, because otherwise you could just pick any constant. So those are not equal, therefore, let's say the absolute value of ni plus 1 minus ni is at least 1. So ni plus 1 minus ni times alpha in absolute value is at least 2. It's at least 2. In fact, it's greater than 2. So what's the conclusion there? That there must be just one k that works. So suppose let's say from d minus 1 being less to ni plus 1 minus ni times alpha less than d plus 1. There is at least one non-zero k, an integer. Oops, flip to the page. At least one non-zero k, an integer, so the k is in this range. We claim there is only one. And that would force the ni's to be an arithmetic progression, and that should break down. Okay, so we've got a plan. If things go right, I can see an end to the question, which would be nice. We claim there is only one such k. Suppose there is a second. I don't know what else. Not k, let's say L. So we'll call it L. So both k alpha and L alpha are in this range. So k is not equal to L. So L minus k in absolute value. So let's say we may assume, or you could say without loss of generality, we may assume L is the greater one. Doesn't matter, they're both just arbitrary names. So L minus k is at least 1. Now, what else can we say? Well, LA minus KA is at most D plus 1 minus D minus 1. And that's 2. Oops. Brought the wrong thing out. L minus K. I keep writing the alpha. L minus K alpha. There we go. I want to write this nicer. So 2, we'll write the 2 first. 2 is equal to D plus 1 minus D minus 1, the bounds of the interval, which needs to be greater than the bigger one in the interval minus the smaller one in the interval, because D plus 1 is as big as the biggest one could get, and D minus 1 is as small as the smallest one can get. But this is equal to L minus K alpha, which is greater than or equal to alpha, which is greater than 2. A contradiction. So K is unique. Therefore, N1, N2, and so on form their own arithmetic sequence. With common difference K. Okay, so now, what can we say from there? Well, then we should be able to show that this can't happen. So we say I don't know, let n1 be n just for simplicity. Then n2 is n plus k, n3 is n plus 2k, and so on. So ni alpha is n plus I minus 1 k times alpha. So that should be n alpha plus I minus 1 k alpha. Okay. So what can we do? Well, consider once again alpha being broken down into an integer part, and beta here is the, we call it the fractional part. I just remind whoever's marking of the way we broke this down earlier in part A. So what do we want to say? We want to say, well, we can find P and Q. Actually, we can just find P with an integer. P is an integer between 0 and k minus 1, so that P over k is less than beta is less than P plus 1 over k. Right, so then I think after a while things will somehow break down in some way. I'm finding it difficult to get the right setup for my contradiction. I know this shouldn't work. I know we shouldn't be able to get an arithmetic sequence for the integers that we're using. I'm just having trouble seeing why. Should I go back to this difference stuff? I think that was fine. It's just you shouldn't be able to keep adding on these betas. Let's think about this again for a moment. So Ni alpha well, actually, hold on. Let's say let's go back to the Ni plus 1 minus Ni alpha stuff. So close to the end, I can feel it. I just don't know where to get the further contradiction. I shouldn't be able to keep on adding k alpha. So that's the issue. So this is n alpha plus, let's say it like this. Ni plus 1 alpha is Ni alpha plus k alpha. So this is Ni A plus Ni beta plus Ka plus k beta. But integers can pop out, so this is Ni plus k alpha plus Ni plus k beta integer part, and eventually this should get big enough so that we get a different value here than one might expect. Should I use another pigeonhole argument? Not entirely sure. I'm not liking what I've written here. So let's try something else. What would a pigeonhole argument even look like? So I think the problem is you can't keep adding k times beta. So I really think we have to sort of look at the first k terms or something like that. The n alpha is fine. It's keep adding on k. This is so frustrating. I'm so close to the end of the contest. Why am I not seeing the right thing? You know, if time ran out, I would probably say, this can't happen, don't have time to explain why. You know, you don't usually get a mark for saying something like that. You usually get marks for saying something intelligent about the situation. And we obviously know that this shouldn't be able to happen because they even tell us there are no arithmetic sequences. But it wouldn't hurt to close off your argument with just oops times up. You get an arithmetic sequence for those. You get an arithmetic sequence for the integer parts. Is there maybe an arithmetic sequence for the fractional parts, then? Let's think about this. So then... Yeah, because it's not just that the n1 and n2 form an arithmetic sequence, then... So n1, n2... and 3 form an arith sequence. Therefore, n1 alpha and 2 alpha form an arithmetic sequence. And before the common difference was k, so now with common diff, k alpha. Okay, so that looks nice. And then the difference of two arithmetic sequences should be an arithmetic sequence. So the fractional part of n1 alpha is n1 alpha minus n1 alpha floored. We'll just say I. So n1 alpha and 2 alpha, because the difference of two arithmetic sequences is itself an arithmetic sequence. So this forms an arithmetic sequence, and now we've got common difference. K alpha minus D, I think. Let's think about that for a moment. That should be the case. Yeah, so K minus alpha, or K alpha minus D. Okay, but then either K alpha minus D is positive or negative. It can't be 0. Alpha is irrational. So K alpha minus D is not 0. So either the n1 alphas and 2 alpha and so on, either these are all increasing, but they're fractional parts, so they have to be between 0 and 1, or they're decreasing. So I guess start with the 1 up here, maybe. and decrease. So it starts big, decreases down. So we have an infinite bounded sequence. This is impossible. Why is this impossible? So k alpha minus d in absolute value has to be bigger than 0. So there is a positive integer. So that positive integer, let's call it, what haven't I used so far? Q. So that k alpha minus d in absolute value is greater than 1 over q. But look at first and q plus first terms. So 1 minus 0 has to be between n1 alpha. It's got to be bigger than the absolute value of n1 alpha minus nq plus 1 alpha. But the difference in those has to be bigger than, so that's got to be at least q times 1 over q. We can even bump this up to q plus second, which is equals 1, so, and this is equal to 1, so we've got 1 greater than 1. This is a contradiction. So our original assumption is there is no infinite sequence. Of these terms. Infinite arithmetic sequence. Okay. So it took a while to get there, certainly. I liked the first half of the question better personally. I liked making those terms and sort of bounding the fractional part. The second part, I feel like it probably could have been done a little faster, but okay, so breaking it down, what did we do? We said, all right, there's an arithmetic sequence of the integer parts, and then we showed there had to be an arithmetic sequence of the n alphas without fractional or integer part or anything added on. I'm saying integer part, I could also say floor function. Or I mean to say floor function. Just usually the double bracket means, anyway, doesn't matter. So, infinite arithmetic sequence of the floor functions gives me an infinite arithmetic sequence of the n alphas, which gives me, to combine them together, gives me an infinite arithmetic sequence of the fractional parts, and the fractional parts are stuck between 0 and 1, so they can't increase forever or decrease forever as an arithmetic sequence, because eventually they'll go past their bounds. Okay, so that's the crux of the argument. It took me a little while to get there, and I was certainly stuck at the end trying to close it all off. I knew I had the right thing when I saw an arithmetic sequence of those n's, of the ni's, but it took me a little while to figure it out. So, okay. Not a bad question. It certainly took me back to my pure math grad courses where I had to do a whole bunch of number theory stuff exactly like this. A little unusual for a contest, but certainly not a question I think was impossible once you, and there might be ways to do it without latching onto this fractional part. I mean, you can certainly look up their solutions. They may or may not use that sort of a thing. But I definitely think pigeonhole argument for A is absolutely necessary somewhere. And I definitely think looking at not the integer, but what's left over is key for both parts. Okay? Whether or not you give that a function or a name, or whether or not you've already known what that function is. But that's going to wrap up the 2013 Open. Good paper. I will see you guys for the 2014 Open if you're curious for more of those. If you want similar contests, things like the Euclid paper by Waterloo is written. The Canadian Senior, Canadian Intermediate Math Contests written about the same time and about the same difficulty as the Open paper. Those are also put out by Waterloo. They're up on my channel. And if you want to get a head start on the 2014 one, that's the next open paper I'm going to be going to next. So feel free to practice that and then join me once those videos are up. So long for now.